Hello physics, here we are with Chapter 9, Homework 3, Problem 6. We've got a bowling ball, we know its mass. We're going to spike it downwards, so we're going to throw it down with some initial velocity from a height of 3.50 meters onto a spring. 7970 newtons per meter is the spring constant of that spring. And we know how much the spring is going to compress before it brings the bowling ball to rest. So we want to figure out what is the initial velocity of the bowling ball. And again, we're going to ignore the fact that the compression of the spring is actually adding to the change in height of this. We could factor that in, but it gets a little annoying. So we're just going to ignore that. We're going to say the total change in height is just 3.5 meters. So, of course, we're going to start off with step 1. So what are we solving for, and what units do we expect it to have? We're looking for the initial velocity of the bowling ball. So V initial is equal to question mark meters per second. That's what we're looking for. Next step, of course, step 1, is to make a sketch. And because this is a conservation law problem, we're going to make 2 sketches. We're going to have an initial sketch that's going to show us what's happening at the beginning of this situation, and we're going to have a final sketch that shows us what's happening at the end of this situation. So initially, what do we have? We're some height above a spring. So there's the spring. There's the platform on top of the spring. This bowling ball is going to land on something. So here's us. Here's the bowling ball. We're spiking it down. We're giving it some initial velocity. So there are speed lines. This is what we're actually looking for. V initial is question mark something meters per second. The change in height is going to be 3.50 meters. The spring constant has, the spring has a constant of 7970 newtons per meter, so it's a fairly stiff spring. The bowling ball has a mass of 7.26 kilograms. I googled it. I think that's actually the mass of a 16-pound bowling ball, so the heaviest bowling ball you're allowed to use. So we've got that. Do we need anything else in this picture? No, I think that's good for our initial sketch. In our final sketch, what do we have going on? Well, the spring is compressed by a height of, by a compression. So if this is the height the spring was at initially, this height here, x final, I keep saying height, I should be saying compression. This compression is 0.300 meters. Let's see. We're up here. Presumably we're pretty happy about everything that's going on. And what else is happening? Notice that there is no longer speed lines on our bowling ball. The bowling ball has come to a rest at the end of the problem. It was moving. It's about to move again, but at this point right now, it is at rest. So I think that's about all we need from this. I can point out that our initial height, the difference in height is 3.5 meters. So what that really means is H initial was 3.50 meters. And H final, that's this height here. This is the lower height, so we're going to have that one be 0 meters. The other one's 3.5 meters higher, so that's why we did it that way. The other thing we know, I'll just write it out just to be explicit. V final is 0 meters per second. The bowling ball is not moving at the end. So I think that's all we need from this. So next step, step 2, is going to be to write the law of conservation of energy. So step 2, sigma E initial plus sigma work external, there isn't going to be any in this problem, we're going to ignore air resistance and everything like that, is equal to sigma E final. So we've got to figure out what kinds of energies we have initially in the first picture. So we're going to ask the three questions. First question, is it moving? Yes, it is moving. There are speed lines. The bowling ball has some initial velocity, so that means it has initial kinetic energy. So KE initial is something. We're going to need a term for that. Second question, is it at a height greater than 0? It is. We're at the higher height, so that means we're going to have GPE. So we have GPE initial. Third question, is there a spring that is compressed or extended? There is a spring, but it is not compressed or extended. So that means in our initial picture, there is no initial elastic potential energy. So we don't need a term for that. So that's the whole left side because, again, there was no external work. So the whole left side is that. Now looking at the final picture. Three questions. Is it moving? No, it's not moving. There are no speed lines. So there's no final kinetic energy. Second question, is it at a height greater than 0? It's not. It's at its lower height, so we're calling that one 0, so we don't have to worry about GPE final. And then the last question, is there a spring that is extended or compressed? There is. We still have the spring, and this time it is compressed, which means there's energy in the spring, which means we do need a term for EPE final. So that's our step 2. On to step 3, which is math. And what math means, basically, is turn all of the things into the things. Sounds a little funny, but that's what we're doing. So kinetic energy. The formula for kinetic energy is 1/2 mv squared. So KE initial is 1/2 mv initial squared plus GPE, that's mgh. And it's GP initial, so I should call it mgh initial. On the right side is equal to is equal to EPE final. EPE is 1/2 kx, let me call it kx final, squared. So now, quick review. I started with the law of conservation of energy. Just a wonderful truth I know about the whole universe. This is true all the time. I apply that to my particular situation, what's going on here. I figured out what kinds of energies I had initially and finally. And then I started getting even more particular about that. I turned the things into the things. KE initial became the first term, GP initial became the second term, and then EPE final became the third term, the one term that's on the right side of the equal sign. So I've got that there. So now I have an equation. I've got a bunch of different terms here, and let's quick peek back at step, what are we actually looking for? We're looking for V initial. So what I've got to do is a bunch of algebra until I have that thing by itself on one side of the equal sign. So the first thing I'm going to do, and there's going to be a bunch of algebra here, so be careful, make sure you're doing it all correctly. So first thing I'm going to do, 1/2 m V initial squared, is I'm going to subtract that second term from both sides. So I'm going to subtract mgh initial from both sides. So that'll give me 1/2 k x final squared minus mgh initial. So that's now on the other side. I'm going to multiply everything through by 2 because I want to kill off that half that's at the beginning there. So that's going to give me mv initial squared is equal to 2 times a half. That's going to go away. That just becomes kx final squared. And then be careful. You have to apply that 2 to everything because of the way algebra works. So a 2 does show up over here. Common mistake is to leave off that 2 right there. Next thing, and I'm running out of space, so let me do it like this. I'm going to divide both sides by m. So that kills off the m on the left side. Make sure you're doing your PEMDAS correctly. You're dividing the whole thing on the right side by m. And then I'm going to take the square root of both sides. And when I'm finally done with that, what that's going to give me is V initial is, really it should be plus or minus the square root of k x final squared minus 2 mgh initial, and all of this gets divided by m. And be careful. In some of these problems, we're dividing by m. It seems like, oh, maybe the m cancels everywhere. It doesn't, because that first term under the square root, the kx final squared, that doesn't have an m, so we can't just get rid of the m. So you've got to keep that and actually plug in the numbers for that. So if I do all this, this is going to give me the square root of k 7970 newtons per meter. X final is 0.300 meters squared. And only that the second part of that, the 0.300 gets squared, not the 7970 part. Minus 2 times the mass of the bowling ball is 7.26 kilograms. G, and I'm going to have to leave off the units because I've run out of space, 9.8 meters per second squared. H initial was 3.5 meters. So let me extend that. And this whole thing gets divided by the mass of the bowling ball, 7.26 kilograms. And just to be clear, that whole thing is all under the square root. So basically, in your calculator, you want to do all of that stuff, and then at the end, take the square root. Make sure you're doing this all carefully. If you're having trouble, do each of the pieces one piece at a time. Do the 7970 times 0.3 squared. Get a number for that. Subtract 2 times 7.26 times 9.8 times 3.5. Get a number for that. Get an answer for the whole top, the whole numerator, and then divide it by 7.26. And then finally take the square root of that. The easiest way to do that on these calculators is by hitting the X to the box button. So I'm running out of room. The button that looks like this. X to the box. There's a button on these TI calculators that look like that. And then the power you're raising it to is 0.5. If you raise something to the 0.5 to the 1/2 power, that's the same thing as taking the square root of the thing. So anyhow, if I do all of this, I'm going to get V initial is equal to plus or minus, it's going to be minus, the ball is moving down at the end, minus 5.50, and it's going to be meters per second. So quick, do step, I solved for the right thing, V initial. I gave it the right units, meters per second. 5.5 meters per second, well, remember the bloody cheetah. If we double that number, we get about 11 miles per hour. That's a reasonable speed to be, spiking down a bowling ball. And it's negative because it's going down. So